Okay, so we're going to look at triangle congruence, and we are going to talk about the ones that we haven't talked about in class yet. So we've actually talked about two in class, and the two that we've talked about are, number one, we talked about side-side-side congruence. If you remember, when we talked about side-side-side, you can abbreviate that SSS. So side-side-side congruence is when we have two triangles and we're able to prove that all three sides are congruent. Now if you remember, when you have these triangles here, once I've proven that two triangles have the same exact side configuration, like all three pairs of sides match up, that's enough information for me to say that the two triangles are congruent. Remember, we talked about it's almost like the Wheel of Fortune. You don't need all three pairs of angles and all three pairs of sides. Just like in the Wheel of Fortune, you don't need all the letters. You just need to chip away and get as many letters as you can until you have enough to show what the entire phrase is. We don't need all three angles and sides. We just need to chip away until we have enough information to tell if these two triangles are congruent. And in this case, showing all three sides are congruent is enough information. So if I wanted to label the congruent sides that I have, it looks like this one's running out of ink here, I would say that AB is congruent to DE, and BC is congruent to EF, and AC is congruent to DF. So those two triangles are congruent by side, side, side. I would then go on to say that triangle, I would make my congruence statement, triangle ABC was congruent to triangle DEF by side, side, side. And what we're looking at here is that the two triangles have the same sides. Now remember, we talked about how we can use the reflexive property and we did a proof. If I have a situation where I have a triangle that looks like this with different colors, if I have this situation, and imagine for a minute that I can actually draw something symmetrical. If I know these two guys are the same and I know these two guys are the same, that's enough information to tell that these are congruent. Imagine this is triangle PQRS. Okay, I can now say triangle, I want to know, is triangle triangle PQS congruent to triangle RQS? We did this on the warm-up yesterday. Well, I'm going to look at the triangle and see if there's anything I can determine in the triangle that I haven't seen yet. And remember, those two triangles share that side. So I know that QS is congruent to QS by the reflexive property. Reflexive property says something's always congruent to itself, and we use that reflexive property when we have a side that's shared. Because we got to imagine that if we take these triangles apart, they both have a QS. So we're basically saying QS in this triangle is going to be congruent to the QS in this triangle. So by the reflexive property, I'm now able to say, yes, they are congruent by side, side, side. So that's how we do side, side, side. Okay. So let's look at now the next one that we did. Just doing a quick review. The second one that we did was side angle side. Okay, so we did side angle side. Now side angle side is where you have, make a little note there, the included angle. Now remember, when we have an included angle, that means that it has to be in between those two sides. It has to be touching both sides. So if I have side angle side, if I draw two angles like this, and in the interest of time I'm going to go a little bit quicker. If these two sides are the same, these two sides are the same, then I can establish side angle side if I have an included angle. So if I mark this angle the same, then I have side angle side. Now, if I name these angles, I name these triangles, remember you have to, your congruence statement has to be in sequence. So if I name the first triangle, triangle HAT, that's congruent to KLJ. You have to go in sequence. When I named the first triangle, I went HAT. I went from 1 tick mark to the angle to 2 tick marks. So I have to go from 1 tick mark to the angle to 2 tick marks for the second one. The triangles are not always going to be drawn like this where they're oriented perfectly for you guys. So here's my congruence statement. And again, look at the angle. Angle A touches both sides, angle L touches both sides. Now, one of the things that we looked at also as an example of side angle side is, remember the bow tie? If I have these two the same and these two the same, the question is, are the two triangles the same? And I'm going to call this A, B, C, D, E. Are the two triangles the same? Well, I don't have enough information yet. I want to know, are the triangles congruent? Well, I've got vertical angles right here, so I can label the vertical angles. So now I have a side angle side pattern, which indicates both triangles are the same. So triangle BCA, and here's where the order is important. I went from BCA, I went from 1 tick mark to 2 tick marks, is congruent to ECD. And that is by side angle side. Okay, so those are the first two. So now let's do the next one that we talked about, which was angle side angle. So we did angle, number 3 was angle side angle, or ASA. Okay, and that's when you have two triangles. And I'm going to kind of draw them in a different orientation just to be mean. You have ABC and you've got DHL. Okay. Angle side angle means that you have an included side. So you have a side that actually has to touch both angles. So that's what angle side angle is. So let's say I have this configuration. This is angle side angle. I have the side included. The side touches both angles. That's very important. So if I were to mark this and use my congruence statement, I would say triangle, and let's say I called the first triangle CBA. The second triangle, if I called the first one CBA, I did CBA. I went from no tick marks to 1. I went through the angle with 2 to the angle with 1. So I have to call this one DHL. And that is by ASA. Okay. Now, we've talked about congruent triangles and using those little reflexive properties. So here's an example of where you might see ASA. Okay. What if these two angles are the same, these two angles are the same, then are these triangles congruent? And the answer would be yes, because what I would end up doing is using the reflexive property. And that would state that PR is congruent to PR. So now I have angle side angle. Whoops, I just wrote something you don't want to see. Angle side angle. I just wrote a bad word. Shame on me. They're going to kick me off YouTube. So that's angle side angle. Now we have two more, and I'm going to give you some notes on these real quick. And I'll do some more detailed notes on these at a little bit later date. The fourth one we have is called angle, side, or AAS, or you can call it SAA. Doesn't matter, either way. And angle, side, we don't have inclusion really. There's no inclusion. Technically there is, but not based on what we're looking at for included. So angle, side would look something like this. If I've got two triangles, if I've got an angle, another angle, and I've got a side, It is a non-included side. If it's a non-included side, then I have angle, side. But be careful. The side has to be attached to the same angle. If this side were attached to this angle, that would not be angle, side. So in this particular one, COW is congruent to TAP by angle, side, or side, angle. Okay? So when you're looking at these, like I said, I'm going to show you an example of what is not angle, side. And my red marker's not working, otherwise I would do the traditional not. So this is not angle, side, or side, angle. If I see something like this, I want you to look at the difference here. This is not side, angle. If you look at this, where is the side marked congruent attached? To the angle with two arcs, right? Where's the side attached here? To the angle with one arc. This is not side angle, or side, angle, or angle, side. That side has to be attached to one angle, but it has to be the same angle. So this side has to be attached to this angle, then that has to be attached to the same size angle in the other triangle. So those two are not congruent. So angle, side does not work here. Now, where would you see an angle, side? Sometimes when you're looking at parallel lines, and I didn't show you an example of this in the other one, if I have that bow tie again, if I make these lines parallel, here's a common deal. If I make these lines parallel, sometimes you'll see it marked like this. And there's a lot of ways you can go with this. You could say the vertical angles are here, or you could not use the vertical angles. What if I wanted to use the parallel lines? I've got alternate interior angles here. So now what do I have? I have angle, side, or side, angle. But let's get a little bit more detailed in this. This is what's nice about these parallel lines. We've worked on these also. These are vertical, right? If I put those vertical angles in there, couldn't I also say angle, side, angle? It just depends on which angles and which sides you choose. Okay? So angle, side can be used when you have the one non-included side, but that non-included side has to touch the same angle. So touches the two, it should touch the two here. It touches the two, it should touch the two here. So it's got to have the same one. Okay, the last one that we have is HL. Okay, HL is the very last one that we have. And HL is called hypotenuse leg, or HL. Now obviously if you see the word hypotenuse, this only applies to right triangles. Right triangles only. Okay? So remember we talked about your favorite word, ass. There is no ass in geometry. You cannot use angle, side. But you can use hypotenuse leg, and it looks like ass. Sorry, I'm cussing on the video. It looks like ASS, but it only works in right triangles. So here's your example, and I'm going to use a different color so we can distinguish. If I have two right triangles, and they're indicated as right triangles. I have a right angle, and I can show that they have the same hypotenuse. Remember, the hypotenuse is the long side across from the right angle. If I can show that they have the same hypotenuse and that they also have a congruent leg, that's enough to say that they are congruent by HL. So I can say triangle PQR is congruent by JKL. Why? Why does this work? Well, you remember for triangles, what do we know about right triangles? What always works for right triangles? The Pythagorean Theorem, right? The Pythagorean Theorem says that leg squared plus leg squared equals hypotenuse squared, right? We commonly see that as a squared plus b squared equals c squared. We can recite that, but the question is, do we know what we're talking about? Well, think about two triangles. If two triangles have the same leg, and they also have the same hypotenuse, which shouldn't be the squared portion, I apologize. Let me write that correctly and circle the correct thing. If they have one leg that's the same and the hypotenuse that's the same, think about the equation. The other leg would have to be the same, right? I can't have A and C be the same thing and get two different B's. So that's why HL works. You're going to see HL quite frequently when you have right triangles. And it looks like the configuration ASS, that's why we don't call it that, because ASS does not